So friends, yes, Nirma Oza again at your perusal with tutorial 23. In the series of protection of transmission lines using distance relays, it is number 11. And theory-wise, probably it is the last tutorial video. Next two videos will be on examples, numericals. How to set the distance relays. What is the setting method of distance relays? And then distance protection will end. So in this series, right now we are discussing problems in distance measurement. Distance relay measures impedance from relaying point to fault point, but it faces many problems. And it seems to me that looking to this problem, distance relay is not that useful. But anyway, that is also sure that distance relay is quite a lot much of use in practice, because line differential is quite costly also. So you can go for line differential protection for 220 kV, 400 kV, 765 kV lines. For lower voltages, probably distance is better. And it is also not so that I've probably listed some 16 or 17 problems. Out of them, only 3 or 4 problems have not solutions as yet. And these problems are not that serious also. That is also the another fact. So now today we are going to discuss last 2 problems. And both difficult. So till today what we were discussing were probably not that difficult. This problem is difficult, and once again, to both of the problems I am not going to use solutions. Solution is in the research world. And fortunately, the research is done by two of my intelligent students. So quite a lot much of material is available. They have worked on it, and that is possible. But right now we will not be discussing the solution. Probably we may hint at the solution, but we may not discuss the solution. It would be too long a video. Probably I think this video, other videos were 15, 20, 30, 35 minutes. This video is going to be little longer, it seems. The problem is protection of compensated lines using series capacitor. You see, people use series capacitor in a line. Why we are using series capacitor? Because we have to think of the equation of power being transferred from sending end to receiving end, from one end to the other end. Sending end is Vs, sending end voltage is Vs, receiving end voltage is Vr. Then power transferred is equal to Vs Vr into sine delta by XL. I am taking XL. I am not taking R plus JXL, because we are talking of very long and high voltage lines. So for 400 kV lines, you can easily ignore R. Therefore, R is ignored. We have taken only XL. Power transferred is Vs, Vr sin delta. Delta is the load angle of the generator. And we have talked about, and you might be knowing, you learnt in machines, that delta, normal angle delta, when the machine is running normally, when it is taking normal full load, that delta is 30 degree. Because you have to give a leeway when the fault occurs, because when the fault occurs, delta is going to increase. And at that time, you see, the system may go out of step. There can be an asynchronous working. Therefore, the limit of delta at normal working is 30 degree. So sin delta cannot be more than sin 30. Sin 30, I think it is half. You can increase the power being transferred from one place to another place by increasing voltages. Yes, we are. And that's what we have been doing. Our voltage was 66 kV. Then we reached to 132 kV, 220 kV, 400 kV, 765 kV. And now in Madhya Pradesh, Bina, 1200 kV is installed, commissioned. But you see, there are enough number of problems of heavy voltage. One voltage is V and Q are related. Q equal to CV. And Q is the coulomb. And that is the reason of a force. If very large charge is there, there are two charges. So transmission lines means two charges. One is line and another is ground. Two charges are there. Or two lines, you can say. So heavy charge is there. If voltage is large, charge is large. And say if you talk of a line and a ground, then because of that heavy charge, there will be heavy force. Coulomb's law suggests that there will be force Q1, Q2 upon epsilon R square. And that stress is on insulator. So insulator may get impaired. Insulator may get damaged. That is the one consequence of higher voltage. Another consequence of higher voltage is corona loss. The corona loss will increase, and corona loss public is not paying, electricity board has to pay. So corona loss is the problem. So increasing the voltage to very high values, and then you have to increase the insulation. If you increase the voltage, you have to increase the insulation. So going on increasing the voltage is not the real solution. No doubt people are using extra ultra high voltages, but better solutions may be there. Sin delta, as I told you, I cannot go beyond delta, I cannot go beyond 30 degree. So what can I do? I can reduce XL. But that itself is contradictory. I want to transmit power, large bulk of power over a long distance of 1000 kilometer and 15 kilometer. Then XL is going to be very high. And therefore power being transferred from one place to the other place is always low. And that is normal power. If you think about fault power, when fault occurs, that is also low. And therefore, if the fault power is high, then there are every chances that the system will go out of shape, will go unstable, will fall out of step, will work asynchronously, and it may lead to cascaded tripping. So then what is in your head? What can you do? So people have found out a way that connect a series capacitor, not only XL. I am talking series capacitor, my friends. Don't make mistake with shunt capacitor. I am not talking about shunt capacitor, which is used for power factor improvement at the receiving end. I am not talking of shunt capacitor. I am talking of series capacitor. So it will be Vs VR sin delta XL minus XC, because C is minus, X is minus. So electrical length of the line gets reduced, and therefore you can transmit more rated power and you can transmit more fault power without uh, losing synchronism, without losing stability. So XC, that is series capacitor, is added to the transmission system network. Usually what is the solution? That people use XL by 2. That is, series capacitor should be half of the line capacitor. So that way you will be reducing the electrical length. It is known as 50% compensation. 50% compensation is done. So if you use series capacitor, so many advantages are there. If you use series capacitor, there are so many advantages. Power transmission capacity is increased. More power can be transmitted between two ends of a line by double circuit also. It is not so that there was no way. But here you can do it by single circuit. So cost will be reduced. So more power you are being able to transfer using a single circuit. That is the another advantage. More fault power also can be transferred. And voltage regulation will be better, obviously, because if capacitor is there, VR is equal to Vs minus IXL. But this is not IXL, IXL minus XC. So that reduces the voltage drop, and therefore voltage regulation is improved. Voltage profile is improved. Voltage profile, it is more sinusoidal, it is more fundamental. The THD, total harmonic distortion, is less. Another thing, series capacitor supplies the reactive power. So reactive power requirement from the generator is reduced. Stability limit of the transmission system network is improved. So these are all the advantages of the series capacitor that you use in the system. All said and done, that brings in problems to our distance protection. That is where we are interested. That where does this bring problem in protection? Many advantages, but very big disadvantage in protection. So if you solve that disadvantage well, the series capacitor is very much advantageous. If you see, series capacitor arrangement is not a simple series capacitor adjustment, because through C, when fault occurs, high current is going to pass. So IXC, the voltage drop, is going to be very large. And that large voltage drop can puncture the capacitor. can damage the capacitor. So, in parallel to capacitor, an MOV, that is the varistor is being used. The varistor means the impedance of the unit, impedance of MOV is voltage dependent. If voltage is small, impedance is large, practically open circuit. And if voltage is very large, then impedance is negligible, practically short circuit. That is the rather characteristic of MOV. Varistor is a metal oxide varistor. MOV means metal oxide varistor. Usually ZNO is used. Zinc oxide is used. But when the current is passing through MOV, the energy is being generated. Energy is being, rather so to say, discharged. If this energy is too large, then MOV also can be damaged. If the fault current is too large. So MOV is also required to be protected. Metal oxide varistor also is required to be protected, and therefore a trigger or a sphere gap is kept so that it will trigger and it will rather protect the capacitor and MOV. And that many times you see when light load is there and when there is no load, then capacitor is not required. So a bypass circuit breaker is also kept. So this is the whole arrangement of series capacitor. It is not a single series capacitor that we are using. Another important thing, series capacitor you cannot keep midway through because you have to maintain it. So it can be kept at one end of the substrate, so either at B end or at A end. So now there are two distance relays R1 and R2. So both these relays, what trouble they are suffering from because of this capacitor. That is our concern. Now you see, if I say so in this concern, now faults are also of different kinds. Triple line fault is a very large current fault. If the fault current is too large, IXC will be very large and therefore it will be practically short circuited. I mean there will be no capacitor because current will pass through MOV only. MOV will short circuit. Voltage across MOV will be practically zero because the voltage across C is large. And if it is so, then it is a normal natural line and then I have not to worry anything about capacitor. Then there is no problem. If it's a high fault current, it's a low resistance fault, then I'm low impedance fault, then I'm very happy because then there is no capacitor in circuit. But unfortunately, the fault is small double line fault at very long distance, large distance, or particularly LG fault, which has got a very small current. Now, what happens that for the small currents, IXC will be small. So, IXC will not be fully shorted. No doubt, MOV will come in picture. The impedance of MOV will decrease. It will not be open circuit. So some current will pass through C and some current will pass through MOV. some current will pass through C and some current will pass through MOV. And when the current passes through C, if there is a fault beyond C for R1, say for relay R1, if there is a fault beyond C, XL minus XC, so fault is seen nearer, fault is seen before capacitor. Fault is after capacitor, but fault is seen before capacitor. That is my problem in protection. That means relay R1 overreaches. That is my problem. For low resistance fault. I mean for high resistance fault or low current faults. High current, no problem. Low current faults, there is a problem. So if you look at the whole thing, it is something like this. That OZ is the real impedance up to fault. But we know that some resistance is always there, so RF. So OZ dash is the resistance measured by the relay. When it is measured, when it is a high current fault, when it's a high current fault, when capacitor is shorted, and then resistance measured is real resistance, true resistance. You have not to think of it, and it will not overreach, it will measure correctly. There is no problem. But if fault is low, very low current fault is Z double dash. So OZ double dash is the very low current fault, because Z double dash is the XC. It will be negative direction. So fault really is OZ or OZ dash, whereas it is seen as OZ double dash. That means it is seen less than what actually it is. And when impedance is seen less than what actually it is, it overreaches. If the fault current is not that very low, it can be in between, then the impedance will lie on that half circle, that semicircle. But you do not know how much current is going to pass through capacitor and how much current is passed through MOB. Because the value of the current is not known to you. When the fault occurs, value of the current is known to you. You cannot predict. You cannot calculate. It is not a subject of calculation. How much fault resistivity will be there in a particular case, you do not know. If you know, then well, you can make a correction factor. You can apply a correction factor and find out the true impedance, but that is not possible. So for low fault currents, it is a big rather problem to the distance measurement. Overreaching of a distance is a big problem. Another problem you see is this, that for relay R2, if you see, for relay R2, if the fault occurs after capacitor, BA line, and fault occurs just after capacitor, then impedance measured is not XL, because XL is practically 0, it is only XC. XC is minus XC. Means your impedance will lie in fourth quadrant and it will be seen reverse. So R2 will not at all correctly measure. That is a another big problem of this compensated lines. So this is the problem of compensated lines, series compensated lines. Solution is given, solution is thought of. Professor Vivek Pandya considered the energy loss at the bus. At the bus, energy that is being lost is different rather than line. In line, loss of energy and loss of energy in bus are different because bus configuration is different. So if you consider that, and if the fault is after the capacitor, means after the bus, then if that energy loss, energy difference is considered, and if it can be calculated, then, then you can apply a correction factor and measure the correct impedance. Another fellow found out another way. You see, if there would have been reactance alone, then overreach would be large because overreach is due to inductance. But if the fault occurs after capacitor, the overreach will reduce because capacitor will reduce the overreach. If you can calculate that percentage overreach and you can apply a formula, you can develop a formula, you can develop an algorithm based on which you can rather find out the correct impedance. I mean, these are the points which are being researched. So we don't talk much about it, but we try to understand that by series capacitor there is overreaches. And the last problem is cross-country faults. I was giving a reason to one of my friends that I would not like to teach nowadays. Because in my days also, when I asked students that what is the cross-country fault, then students replied, a student used to reply that when fault crosses a country, then it is known as a cross-country fault. If fault crosses from India to Pakistan, then it is cross-country. So students are so weak. You see, electrical item has nothing to do with geography. What is cross-country fault? Cross-country fault is two different kinds of faults occurring on the transmission system simultaneously at two different locations. Say, for example, there is 100-kilometer line followed by another 100-kilometer long line. There are two lines, 100 kilometers, second. At 80 kilometers on the first line, double line fault occurs, RY. And in the another line, at 60 kilometers, that means from initiation of the relay 160 kilometers, YG fault occurs. So relay sees that as an RYG fault. And unfortunately, neither at 80 kilometers nor at 160, but at the probably average of the two, 80 plus 160, that is 240 divided by 2, so 120. So it sees at 120 kilometers. 80 kilometers was within the zone, first zone, whereas it will be seen in second zone. So delay will overreach for that fault. And 160 kilometers is seen at 120. It is under reach. It should not have operated, whereas it is operated. So this is, and I am not talking about RY and YG. You can talk about any RG and YG. You can talk about RYB and BR. You can talk about RY and YB. Any two different kinds of faults occurring at two different locations simultaneously on transmission line. That is cross-country fault. My good friend and my student, Dr. Vijay Makwana, has hinted at this problem in his PhD thesis. If somebody is interested to go through the full solution, you can read his thesis. Here, it would be too much to go to the solution of such problem. But problem is there. So, distance relay is creating so many problems that we were thinking that distance relay is very good. But it is not that good, and it creates many kinds of problems. But this is all non-switch relays. We have used 6 different relays. There is another scheme of switched distance relays. What is switched distance relays? That there are no 6 units. There is a single unit, but 4 procedures, 4 calculations. In the relay algorithm, there are 4 logics. One is classification of fault. First logic will classify the fault, whether it is RY fault, YB, BR, RG, YG, BG. Not very difficult, no? In whichever phase the fault occurs, that current is going to increase and voltage is going to collapse. In the phase where there is no fault, current will not increase and voltage will not collapse. So classify the fault. Once the fault is classified, you know that is RY fault, then that is true that you will need those quantities. So you have to keep the quantities ready. Your CT and PT. So VRY and IR minus IY you keep ready and feed it to the relay. So first you should know that it is RY fault. Then feed VRY and IR minus IY. After dividing VRY by IR minus IY, if you find that the impedance Z, that means you have to measure the impedance using this. And if this measured impedance is less than the set impedance, then final tripping signal is to be issued. These 4 steps are required to be done. In earlier days, people did not use switch distance relays because to pass through all these 4 procedures was very time consuming. Rather than that, what people did? People did this. Connect all 6 contacts in parallel. Whichever operates will trip this breaker. Right? So that was done in earlier days. But now, because you see, the numerical relays have come up and it is taking their sampling time is 1 millisecond. Within 1 or 2 or 3 milliseconds, it can do one step, say classification of this. So within few milliseconds, maximum within a cycle, it will find out whether there is a fault or not, and it will be able to give a signal to the breaker if the fault, if the other it is necessary to treat. So because of fast digital signal processors, because of fast processors, microprocessors, because of fast mathematical techniques used in numerical relays. Most numerical relays now, or I should not say mostly all numerical relays invariably now use switch distance relay, in which all these 4 procedures, 4 steps are required to be done. So this we have seen, right? So with this we see what are the facilities provided in numerical distance relays. Latest numerical distance. They provide starting. That is whether the fault is there or not, how you can know. So a starter is there. So there are three kinds of starters. Overcurrent starter, because if the voltage occurred, overcurrent or earth fault will increase. Under voltage starter, because voltage will collapse. And under impedance, because impedance will reduce. Any of these three starters can be used, right? So this is the one facility. Then another thing is, when closing fault occurs, the voltage memory is possible, is much more easily possible in numerical relays. Provision for reverse looking zone. You can have a reverse looking zone, reverse looking mode zone. And we will discuss carrier, we will discuss this. In carrier aided distance scheme, this reverse looking zone is required. That is fourth zone. We were talking about three zones only. So this is fourth zone. So this is possible in numerical ways. Monitoring of current and voltage circuit we have discussed. That is possible in numerical ways because it is logical. It is programmable. Things are programmed. Backup power current protection you can add and switch on to fault. Switch on to fault means if the fault is already existing when you rather fault is really existing when you make the circuit breaker on. You see, it is not circuit breaker on and fault occurs. It is reverse. Fault is already there and you made the circuit breaker on. Now, when you know that fault is already there, why to take time? When we already know that fault is there, then the fault can be cleared instantaneously. So if the fault is existing anywhere, when you switch on the fault, switch on the breaker, then this breaker will trip instantaneously. That is the switch on to fault facility. Right. So another problem is this. That is what we are talking, no? That if earthing switch is on and circuit breaker is inadvertently made on, then voltage will be zero and distance protection cannot work. So the voltage memory function is there in the numerical that can be used. And much worse is the CB1 is closed. It is not open. Sorry, it is not closed, it is open. And line is being maintained. Now line maintenance is complete. Somebody forgets to open ES2, earthing switch at another end, and makes the CB1 on. Between CB1 and ES2, there is no interlock. So this is possible that this mistake can be done. So this is switch on to fault and circuit breaker will immediately operate in this case. Circuit breaker will operate quite immediately in this case. Carrier signal can be given binary input. Carrier signals, carrier equipment will be required. That is true, right? Big carrier system is required. But this carrier system can be routed through numerical relay so that you do not need another ancillaries, another equipment. This numerical relay itself can be used to route the carrier signal through it, and you can use this line differential protection in numerical relays. Circuit breaker failure protection, which we already start facility we have talked about. Measurement of current, voltage, frequency, active, reactive power, apparent power, energy, impedance. Everything can be measured. We have talked about all these things. Following records are available and fault occurs. And 32 Faults can be memorized in Brilliant version release, REF 615, RET, REV, REG. Fault current, faulted voltage, fault angle, fault distance, fault impedance, and operating time. So many things can be recorded. Little lengthy, little difficult also, little complex also, my friends, I'm sorry. This problem is complex and difficult. And therefore, so often I wish I don't teach this problem to the students. Students cannot understand. Students are not being able to understand many things which I teach. So often I feel that the teaching which is not understood has no meaning. So this problem was quite difficult. Solutions are yet very difficult. I have not yet discussed. But at the end, we will see a sentence. He who depends on chances and situations to be happy is a sansari. संसार में जो रहता है, जिसकी पत्नी है, जिसके बालक है, जो बाजार में जाके, the person who goes to the market and takes wheat, etc., the person who has got wife, the person who has got kids, is not sansari, is not the real definition of sansari. The real definition of sansari is you are dependent on chances and situations. What kind of chances are coming to you? And what situations? What situations you are thrown in? Good situation, bad situation. If you are above both these things, chances and situation, then you are sannyasi. Then you are sannyasi. Spoken by some saint. So, friends, one has to try to become less sansari and more sannyasi. If not full sannyasi, partial sannyasi and partial sansari. Don't get affected by bad situations and don't be happy by good situations because this will also pass away. So with that, my friends, I will remember my dear Adapt Me, and I would request you to share to all your friends this video, ask them to read, ask them to hear the video. This is the last video in the series of distance protection as far theories are concerned. Next two videos we will be doing the examples, numericals on how to solve how to set the distance relays. Then distance relay will be completely over. Thank you and goodbye.